Hello everyone, thank you very much for watching this video, and thank you to the organizer of the Early Universe from Home conference. I'm Thomas, I'm a postdoc from Cambridge, and today I will say some words about constraining dissipative inflation with open effective field theories. The topic of this talk is the fact that even if single field throw inflation is a very compelling scenario for the physics of the primordial universe, there exist scenarios in which the inflaton field exists on top of other sectors that we cannot observe directly. Such an example was proposed in this paper by Paolo Criminelli and collaborators, where the inflaton field coupled to another massive scalar field with a particular symmetry breaking pattern. And in this type of scenario, the main matter is the fact that the gauge sector gets populated by an instability and then plays the role of an effective bath for the inflaton field. That makes that whenever we try to model the dynamics of the perturbation that we want to later on observe in the sky, either in the cosmic microwave background or in the large-scale structure of the universe, its dynamic features some dissipation corresponding to the dumping of energy of the inflaton fluctuation into the bath made by the gauge sector, and some fluctuation or noise that comes from the fluctuation of the bath, leaving imprints into the inflaton perturbation. And so modeling the interplay between these two effects is difficult. It in general goes through a set of nonlinear stochastic differential equation that we call Langevin equation, where you need to specify a set of stochastic variables that correspond to the fluctuation of the gauge sector back reacting onto your system. So this type of dynamics is quite rich, with a rich phenomenology, but it's also hard to model. And so the question that is at the heart of this presentation is trying to understand if there exist general rules of universal prediction or typical smoking gun that would help us to identify whether this is a scenario that could have taken place in the early universe or whether it's disfavored by the data. And so in our case, the approach we have followed to try to model this class of model in a generic fashion is to combine techniques from particle physics known as effective field theories with techniques from condensed matter and quantum optics known as open quantum system. Open quantum system is a set of techniques that has a long-lasting history. It started in the 19th century with the study of Lord Brown of pollen particles immersed into water. And the goal is to model the erratic trajectories of this particle in a medium. In our case, the particle is the inflaton field and the medium is the surrounding bath made by the gauge sector. Even if these techniques were initially developed for statistical field theory, they were later on extended to quantum theory and to relativistic QFT. And so our goal is to combine some of these techniques, such as the master equation or the influence functional, to say something about primordial cosmology when we merge them with the effective field theory of the early universe. In particular, open quantum system will bring the understanding of dissipation and noise, while effective field theories help us to understand in a systematic fashion scalar hierarchies and symmetries. And so to give you a very concrete example of what I will describe in these slides, the idea there is that the EFT of inflation was a way to describe single clock model of inflation. And by constructing an open EFT of inflation, we enlarge the class of model and physical phenomena that we can describe by this approach in order to also capture local dissipative model of inflation that emerge and sort some of this gauge inflation scenario. And that also help us to model classes of inflation such as stochastic and warm inflation. So that's the goal of this presentation. Now the way it will work is that I will first introduce this generic construction, then I will discuss its phenomenology in terms of primordial non-Gaussianities, and I will conclude by some complementary probes by using primordial gravitational waves. So let's start with the construction. In this paper, we have considered a particular scenario which is fairly simple, in which we assume that we have a strong Sorel hierarchy. And when we have a strong Sorel hierarchy, in the language of the EFT of inflation, it means that we can work in a particular limit that we call the decoupling regime, where in terms of the scalar sector, we can focus on one single scalar adiabatic degree of freedom that I do not pi, while neglecting the perturbation of the metric. It means that when we come to our colleagues that work on CMB physics, what we need to give them are theoretical predictions for the endpoint function of the scalar field that we call the cosmological correlators. And to know this endpoint function, we need to know the statistics of this field. What has been doing the usual EFT of inflation is to provide these statistics in terms of the most generic wave function. And at a very technical level, it amounts to perform this type of single branch path integral, just as we do, for instance, in collider physics. Now, the input from our colleague from condensed matter and quantum optics is this understanding that if we want to model dissipation and noise between this pi field and a surrounding environment made, for instance, of this gauge sector, then we need to work with a slightly more generic object than a wave function. That is called a density matrix. It's an object that accommodates pure state, but also mixed state, where some information has been lost in the environment. At a technical level, it amounts to perform this double branch path integral that we call the Schwinger Keldysh path integral, where some operator will mix the two branches of the path integral, coming from the effect of the surrounding medium onto my system. Despite this difference of going from a single branch to a double branch path integral, the strategy remains the same. That is, we can still use unitarity or symmetries or locality to restrict the shape of the object that appear in our path integral. And this is the game we will try to play to construct this influence functional in the most generic fashion. In particular, the main aspect I would like to discuss here is the symmetry theory in this Schwinger-Keldysh contour. The idea is that if I work in this double branch path integral, a priori, if I work in a theory where I have no mixing between the branches of the path integral, then I have two copies of the field, one for each branch of the path integral, and two copies of the symmetry group, one for each branch of the path integral. For instance, in the construction I presented before, in the usual EFT of inflation, we have two shift symmetric scalar, one for each branch of the path integral, with two copies of the shift symmetry. Now the point is that when we include dissipative and stochastic effect that imprint the effect of the surrounding environment onto the system, this will generate operators that mix the branches of the path integral. And because of this operator, we will in general break two copies of the symmetry group to a smaller subgroup that is the only remaining symmetry that is consistent with this operator mixing the branches of the path integral is the one where we transform the two branches of the path integral by the same amount that we call the retarded symmetry. On the contrary, the transformation that transforms the two branches of the path integral in opposite direction has been broken by the inclusion of the dissipative and stochastic effect. And so that makes that instead of having two shift symmetric scala in the dissipative theory, I have only one of them, and decompose into this basis of the mean between the two branches of the path integral and the difference between the two branches of the path integral that we call the retarded and advanced basis, we observe that only the retarded component shifts under time translation symmetry, while the advanced component just transforms as a regular scalar. So that will be the main difference between a closed theory and an open theory. And it makes that now we have identified our building block to write down a dissipative shift symmetric scalar in a de Sitter universe. Now that we have our building blocks, we can write down our most generic functional. And first, at linear order in perturbation, what we observe is that it contains more operators than the usual EFT of inflation. For instance, on top of a kinetic term that is already there in a unitary theory, we now have some form of dissipation that encodes the damping of energy from the pi field into surrounding medium, and different noise operators that correspond to different direction in phase space of fluctuation of the surrounding medium, leaving the imprint onto the pi field. We can go on and write down the cubic operator. Indeed, we have no more coefficient to take care of. Importantly, the EFT of inflation was known for relating operators at different orders through nonlinearly realized boost. And here the same holds true not only for the unitary direction, but also for the dissipative and stochastic direction, as it was already noted more than 10 years ago in this paper by Lopez-Nassier and collaborators. So the take-home message is that it's a systematic construction that allows us to recover in a certain limit the usual EFT of inflation, but also extend it by capturing the effect of local dissipation and noise. Now the next question is, what's the expected phenomenology for this class of model? And I will first start to talk about primordial non-Gaussianities. You may wonder why we don't talk first about the power spectrum, that is, the Gaussian statistics. And the reason is that because of the symmetry input we have taken in this construction, we are sure that we will obtain a nearly scale-invariant power spectrum. That means that by imposing a scale hierarchies among the various parameters that appear in the theory, we can already reach a nearly scale-invariant power spectrum that fit the data for the early universe. On the one hand, it means that this class of theory is compatible with the observations so far. On the other hand, it also means that we cannot distinguish this class of model at the level of this two-point function. I should emphasize that still there is a very important conceptual difference, is that in the usual single field through inflation scenario, the origin of the scalar perturbation is from quantum mechanical origin, whereas here it's rather coming from classical fluctuation of the medium that backreact on the system and leaves the statistics. So it's really two different mechanisms of generating perturbation. If we want to see something more specific of this type of dissipative dynamics, we need to go for the non-Gaussian statistics. And in particular, we started by looking at the bispectrum, that is the three-point function. We compute this quantity perturbatively using a set of Feynman rules, which are written here, where there are a few subtleties compared to the usual theory, in particular the fact that we have two different types of propagator, so-called retarded green function and the so-called Keldysh green function. But apart from these subtleties, it essentially works the same. And now the object we compute is this three-point function of this curvature perturbation that we characterize in terms of the object called the bispectrum. In general, phenomenologists consider two aspects of this function. First, its kinematic dependence in terms of K1, K2, K3, or alternatively in terms of X2 and X3, which are the ratio of K2 over K1 and K3 over K1, because since you have scale invariance, you can remove one of the variables. The other quantity that matters in this story is the so-called FNL parameter, which tells us the amplitude of the signal in a given configuration. So let's first discuss the shape. In this class of model, what's important is that there are mainly two regimes. One at large dissipation, which corresponds to the orange curve in this plot, where the dissipation parameter is much bigger than the Hubble parameter, and the signal peaks in the so-called equilateral shape, correspond to the situation where K1 equal K2 equal K3. And it's a feature that is fairly generic in many classes of model. For instance, it's what we expect also from a small speed of sound in the usual EFT of inflation formulation. Therefore, a priori, the signal is degenerate with other classes of model in this regime. On the contrary, at low dissipation, where the dissipation is much smaller than the Hubble parameter, the signal peaks in the so-called folded configuration. This is what we can see in this blue curve in here, where the signal peaks in this type of flattened triangle. And this is a much more peculiar signature for this class of model. It does not have many overlap with other inflationary models. For instance, it overlaps a little bit with non-Bunch-Davis initial condition, but the main difference is that in our construction, because of the symmetry input, we always fulfill the consistency relation. That is, the signal vanishes in the squeeze limit, where one of the mode is taken to be very small. And so that makes that this type of phenomenology, where we interpolate from a folded configuration to an equilateral configuration, has not a very large overlap with the type of templates that have been already studied in the context of primordial cosmology. That motivates some of our colleagues to try to understand what are the constraints we can place using the current data on this type of inflationary model. And this is a project that is ongoing in collaboration with two brilliant PhD students in Cambridge, Bowe Zhang and Peter Suman, that have been working in trying to adapt this so-called modal pipeline that is a way to place constraints on inflationary model using Planck data. A question we ask in this project is, what are the constraints on these two parameters that control the linear dynamics, the speed of sound and the dissipation of the scalar field pi, in order not to overproduce primordial non-Gaussianities? And the preliminary results are in these two figures. What you can see in here is in red the theoretical prediction from a particular value of CS, the particular value of the dissipation as function of this FNL parameter, whereas the blue curve corresponds to the data prediction when we project the data on the particular shape expected for this value of the parameters. What we observe is that at large speed of sound, you need to go at very high value of the dissipation before you overproduce non-Gaussianities. Whereas at small value of the speed of sound, you tend to amplify the non-Gaussian signal, which makes that you escape very quickly the region that is allowed in the parameter space to remain compatible with the lack of observation of primordial non-Gaussianities so far. So that's not much, but that's a starting point to place some constraint on this class of model using primordial non-Gaussianities. In the last part of this talk, I'll say a couple of words about primordial gravitational waves. So far, we described the dynamics of a dissipative shift-symmetric scalar in a quasi-de Sitter universe, but we were not able to say something about the regime of validity of this construction, in particular the decoupling limit that we took. Now, what's the dynamics of gravitational waves in the medium? That's why we extended this theory by having this type of construction that we call open gravity, where now the system is made of the metric and some matter sector, for instance, our inflaton field, where the environment is some other stress energy tensor, for instance, our gauge sector. And we hope we have a suitable scale hierarchies that allows us to model the interplay between the two in terms of an open effective field theory. Just as always in the Schwinger-Keldysh contour, the fields are doubled, which means that we have two copies of the metric, one for each branch of the path integral. But we also add two copies of the symmetries, and in particular, two copies of the diffeomorphism invariance. So the way we model dissipation and noise is, again, relying on some knowledge from condensed matter and quantum optics that treat dissipative gauge theories through a particular symmetry breaking pattern that we call a strong to weak spontaneous symmetry breaking pattern. It essentially works just as we did before for the shift symmetric scalar, where we take the two copies of the diffeomorphism invariance, break it to the diagonal subgroup in order to open the theory, and eventually further break it if we want to introduce more dynamical degrees of freedom as a clock field, just as we do in the usual EFT of inflation. In this type of approach, it does not mean that we have explicitly broken any gauge symmetry, but rather that we are constructing the theory in a convenient gauge that is like a unitary gauge, and that we can always restore full covariance by performing a set of Zuckerberg trick. Now that we have the symmetry breaking pattern, we can describe the dynamics of the various components of this problem, and in particular, the dynamics of the linear transverse stresses perturbation of the metric is given by this type of Langevin equation, where we can see four types of physical effects: the appearance of some speed of sound, the dissipation next to the Hubble drift that corresponds to the dumping of gravitational waves propagating through the medium, some form of birefringence that will treat the two polarization in different fashion, and interestingly, it comes with fewer derivatives than the unitary effect. That's why we call it dissipative birefringence. And at last, some stochastic variable that correspond to the noise from the tidal deformation of the medium, leaving some primordial gravitational waves. We have studied the phenomenology of this class of model in the case when there is no birefringence. That leads to this figure where we have the tensor to scalar ratio as a function of the dissipation affecting the gravitational waves and different values of the noise sourcing the gravitational waves. The red shaded region corresponds to observational constraint from the lack of observation of primordial gravitational waves. And so by using the result from the biseparate collaboration, we can place some upper bounds on the maximal amount of noise that can source gravitational waves in the early universe. That's not much, but it's again another way to constrain this type of dissipative dynamics in the early universe. So that brings me to my conclusion. In this talk, we presented a theory called the open EFT of inflation, which is a way to implement the constraint from unitarity, locality, and scale invariance in order to describe dissipative components in the early universe. This is a way to describe certain type of gauge inflation models in the presence of scale hierarchies, such as dissipation and noise can be described as being local. In terms of primordial non-Gaussianities, its main feature is to generate some signal at low dissipation in the folded configuration. That is relatively peculiar and that we hope to detect, or at least to constrain using CMB and LSS data. At last, in terms of primordial gravitational waves, we've seen that this is a way to model gravitational waves that experience damping and sourcing from a medium, and we hope that we can further use that to say something about the generation of gravitational waves through the interplay between inflaton and gauge sector in the early universe. On this word, I thank you for your attention, and I'm very happy to discuss further in the days coming. Thank you.